You know, for all of human history, we've looked up at the stars, and they've just been these distant, untouchable lights. But what if that could change? What if we could actually send something to another star system? And I don't mean in thousands of years. I mean within our lifetime. Well, that's exactly what we're going to break down today. The incredible, audacious engineering plan to make it happen.
It really is the ultimate question, isn't it? How do you get to another star? It's the stuff of science fiction. The distances, they're just mind-bogglingly huge. But the answer, and this is the cool part, might be to think really, really small and to move unbelievably fast.
And when I say fast, I mean fast. We're talking 20% the speed of light. Let that sink in. That's not a typo. 20%. That's 60,000 kilometers a second. At that speed, you could get a probe to our nearest stellar neighbor, Alpha Centauri, in just about 20 years. A 40 trillion kilometer trip in 2 decades. That's a game changer.
Okay, so how on earth is this possible? Here's how we're going to tackle it. We'll start with just how impossible this dream seems. Then we'll look at the Starshot solution. After that, we'll dive into the epic engineering puzzle, see how they're modeling a breakthrough. And then, the big reveal, the actual blueprint for this starship. Finally, we'll look at what this means, the next giant leap for all of us.
All right, first things first. Let's just try to wrap our heads around the scale here. Alpha Centauri, it's 4.37 light-years away. That number sounds neat, but it's over 40 trillion kilometers. Our fastest spacecraft, like the Parker Solar Probe, it would take tens of thousands of years to get there. So yeah, to do this in a human lifetime, you can't just build a better rocket. You need something completely different.
And here's that completely different thing. Forget the Starship Enterprise. This is a nanocraft. It's a tiny, gram-scale probe on an ultralight sail. The whole package, sensors, camera, everything, weighs about the same as a paperclip. Seriously, the real genius here isn't the ship itself, it's how you get it moving. So, the big idea? You leave the engine at home. Yep, instead of lugging around tons of fuel, this tiny nanocraft gets pushed by a giant laser array right here on Earth. This beamer fires an incredibly powerful beam of light at its sail, and that's what sends it flying. This whole concept is called beamed energy propulsion, and believe it or not, the idea has been kicking around for a while.
Yeah, this isn't something someone dreamed up last week. The basic concept goes all the way back to 1962, with a physicist named Robert Forward. But the real breakthrough, the thing that makes it all possible, came later. See, the early ideas were to use metal sails, but they would just instantly melt under a laser that powerful. The solution? These advanced materials called dielectrics. The simplest way to think of a dielectric is like an almost perfect mirror. When that intense laser beam hits it, nearly all the light bounces off as propulsion. Almost none of it gets absorbed as heat, and that is the secret sauce. That's what lets it survive the blast and reach those insane speeds.
Okay, so the physics checks out. Great. But now comes the really hard part. How do you actually build this thing without bankrupting the entire planet? You could design the system in a million different ways, but almost all of them would be ludicrously expensive. So the real challenge, the epic engineering puzzle, is this three-way battle against cost.
At the end of the day, the price tag comes down to this tricky balancing act between 3 main things. You've got the lasers that make the light, the huge optics that aim the beam, and the energy storage you need for that one massive pulse. And here's the catch. They're all connected. Try to save money on the optics by making them smaller? Well, now you need way more powerful and way more expensive lasers. Try to cheap out on the lasers? Now you need a bigger, pricier optical array. It's this constant, wicked trade-off.
And this all comes back to the sail material. It's the linchpin of the whole operation. The old ideas using metal sails, they were just a non-starter. They would absorb way too much heat and just poof, vaporize. The absolute game changer is the dielectric sail. It absorbs something like 5 orders of magnitude less energy. That means it can take a hit from an unbelievably powerful laser and survive. And that allows for just insane acceleration, turning what would have been a years-long push into a launch that's over in minutes.
So how do you solve that impossible 3-way cost problem? You can't just build a bunch of different versions to see which one's cheapest. That would cost trillions. So you don't. You do what modern engineering does best. You build a digital twin. You create this incredibly sophisticated computer model that lets you test everything virtually. This is what takes the project from sci-fi dream to plausible mission.
And the whole point of this model is just genius.
It completely replaces incredibly expensive real-world experiments with pure simulation. I mean, just think about it. You can't just go out and build a kilometer-wide laser array as a test run. So instead, this model lets the engineers play in a digital sandbox. They can tweak every single variable you can imagine, the sail size, the laser power, how long the launch is, and they can run thousands of these virtual missions, all to find that one perfect sweet spot, the single combination that gets the job done for the absolute lowest cost.
And the way it works is actually pretty straightforward, but it's super powerful. Step 1, you tell it the goal, let's say 20% the speed of light. Okay, then, for any given design, the model simulates the entire trip, calculating exactly how much power it needs every single millisecond. Then it spits out a price tag for that specific setup of lasers, optics, and batteries. And here's the magic part. It just does that again and again and again, thousands of times. It keeps tweaking the variables, searching for that one design that hits the target speed for the lowest possible cost. It's like a computer searching for the needle in a haystack and finding it.
So, after all those thousands of simulations, what's the answer? What does the perfect, cheapest mission actually look like? Well, the numbers that the model came back with are, honestly, they're just breathtaking. This is it. This is the blueprint for humanity's first real starship. First up, the big one, the price tag. The model predicts the total cost to build the ground-based laser array is about $8.3 billion. Now, don't get me wrong, that is a ton of money, but it's in the same ballpark as other huge science projects like the Large Hadron Collider or the James Webb Space Telescope. It's not fantasy money, it's actually achievable. Okay, now for the ride. The acceleration this little craft experiences is 15,200 Gs. To give you some perspective, that's the same kind of G-force a bullet feels inside the barrel of a gun. It is an absolutely brutally violent kickoff. So how long does this insane bullet-like acceleration last? An hour? A day? Nope, just 10 minutes. That's it. In literally the time it takes you to make and drink a cup of coffee, this thing goes from 0 to 20% the speed of light. After that 10-minute push, it just coasts. It's on its way, silently traveling through interstellar space for the next 20 years. And what's doing the pushing? This beamer, the laser array, would have an effective diameter of 2.7 kilometers. I mean, that is a massive piece of engineering. We're talking about something on the scale of those giant solar power plants you see out in the desert, like the Crescent Dunes facility. Just a huge, powerful structure. So let's put it all together. Here's the final blueprint for the big mission to Alpha Centauri. You've got a target speed of 20% the speed of light. The beamer costs about $8.3 billion to build, the sail itself is about 4 meters across, carrying a craft that weighs less than 4 grams, and the power needed? A staggering 200 gigawatts. But here's what's really wild to me. The energy cost for each launch is only around $7 million. Once the big laser is built, actually sending these probes becomes, well, relatively cheap. And what's so cool is that this tech scales down beautifully. Before we go for the big one, we could build a smaller precursor mission for around $500 million. This little guy would only get to 1% the speed of light, using a sail that's just 19 centimeters across. But that's the perfect test run. It's how you prove the concept right here in our own solar system. At that speed, you could get to Mars in a single day, or all the way out to the Kuiper Belt in a month. Just incredible.
You know, this is about so much more than just one mission to one star. If we can master this kind of beamed energy propulsion, it would completely change our relationship not just with the stars, but with our own solar system. It is a genuine paradigm shift in how we think about space travel. Just think about the future this opens up. We could have a constant pipeline of these little probes, sending one off to a nearby star every few weeks to get more data. Travel time within our solar system would be completely slashed. And get this is a wild side effect. At 20% the speed of light, the probe is moving so fast that it could actually use the sparse gas and dust of the interstellar medium as a power source. It's mind-bending.
So what's the absolute theoretical limit here? Where could this technology ultimately go? Well, the author of the paper we're looking at, Kevin Parkin, did the math. He calculated that if you could build a beamer the size of London, you could push one of these nanocraft to over 90% the speed of light. We are talking about entering the true realm of relativistic travel. It's just staggering.
So, here we are. For the very first time in history, we have a real, viable engineering plan to actually reach another star. The tech is getting there, the physics works, the path is clear. It really just leaves us with one final, thrilling question.